Hello, Five Side family. We're back. We are going to be learning about light waves and how they are actually electromagnetic waves. Let's go. Looking at this picture real quick, we know that if we shake the end of a stick in a puddle of water, you are going to get that rippled wave effect. All right, but similarly, if you shake a charged rod, so say this rod in the air, shaking it back and forth in empty space, you're actually going to create a magnetic field as well as an electric field, which is going to eventually turn into what we call an electromagnetic wave. Let's explain what those actually are. So electromagnetic waves, though everything's explained up here, if you take a look at this picture down below, this really helps. All right, so if we have a current flowing through a wire, we know that moving current actually creates a magnetic field. But when we have a magnetic field that moves, it also creates an electric field. But by having an electric field, it creates another magnetic field. And therefore, that creates an electric field, which creates a magnetic field back and forth. That idea gives rise to what we call electromagnetic waves, which is what light falls under. If you take a look at this picture, electromagnetic waves are really just an electric field and a magnetic field being put together and oscillating. So if you take a look at this, this is your electric field going up and down oscillating, and perpendicular to that would be the magnetic field. Notice that the magnetic field gets larger as your electric field is getting smaller, and they kind of go back and forth. Now this is more of a 3D type of drawing in a two-dimensional shape, and we don't want to get too far into what electromagnetic waves are because we're just kind of scratching the surface. But if you hear the term electromagnetic spectrum or electromagnetic waves, just to understand that those waves that create light are actually a mixture of an electric field and a magnetic field. And because they regenerate each other, it forms this wave-like oscillation. Now this is a picture actually of a Khan Academy, and if you look on Canvas or whatever I have linked here for class when you listen to this, but it actually is a good video that explains how electromagnetic waves are formed. So check that out. The link is on our online class, probably through Canvas. All right, so electromagnetic wave velocity. Since we know that this electromagnetic induction is occurring, meaning that an electric charge is creating a magnetic field, which creates an electric charge, which creates a magnetic field, and we know that, of course, the energy of conservation happens, the speed of an electromagnetic wave is going to stay constant. The reason for that is you're not going to gain or lose energy. The energy from the magnetic field is going to create the electric field. That energy from the electric field is going to create the magnetic field. So there's no rise or fall in energy because of the conservation of energy. Therefore, if there's no rise or fall in energy, the wave isn't going to speed up or slow down. It's going to go at a nice constant velocity. So that's why we can give all electromagnetic waves the same speed, which is the speed of light. The speed of light is 300 million meters per second. We note the speed of light with the letter C. You may remember it from chemistry. E equals mc squared. C was the speed of light in that important Einstein equation. But the idea here is that light, or any type of electromagnetic wave, travels incredibly fast. Again, in your head, try to think of 300 million meter sticks. That's how far one electromagnetic wave will go in 1 second. That is a huge amount of distance in a short amount of time. Humans cannot travel at the speed of light yet. Obviously, we can break the sound barrier and travel faster than the speed of sound, but the speed of light is out of our reach. We can get particles and particle accelerators and atom smashers almost up to that speed by using high-tech magnets turning on and off and basically colliding them with other charged particles or elements to try to create new elements. But anyways, the speed of light is incredibly fast. All right, so why do we talk about electromagnets? Because in electromagnetic waves, it's because of the spectrum. We can only see the visible light spectrum, which is the rainbow. But weaker energy than what we can see is the infrared, the microwaves, and the radio waves. Notice that these guys have longer wavelengths, which means that they have lower frequencies and actually means that they have lower energy. Over here, just above purple or violet is ultraviolet, which is like the UV rays from the sun. Then stronger is X-rays, and then the bad stuff, gamma rays. Notice that over here the wavelengths get shorter, which means their frequencies increase, which mean the energy increases. That's why on this side of the electromagnetic spectrum it tends to be higher energy, more dangerous, and on this side of the electromagnetic spectrum these waves or light tend to be weaker. Now please remember that we can only see the visible spectrum, but all of these are considered forms of light or electromagnetic waves. We can't see infrared light, we can't see microwaves, we can't see radio waves, but we know they're there. If you tune up your radio to a radio station in your house, you pull up, 96.3 or 103.5. Why? Because those radio waves are around us and bouncing around. So they're always there, we just can't see them. So we actually see very, very little of the world around us, believe it or not. Here's another example of the electromagnetic spectrum. It is just trying to give you ideas of how long those wavelengths are. For example, when you get into radio waves over here, the length of the radio waves could be as long as a soccer field or as short as a baseball, right? When you get to the other side, like X-rays and gamma rays, now we're getting into things the size of molecules and a nucleus, so very, very, very tiny. But take a look when you can. Pause this video and take a look at the spectrum and try to learn all about what's going on with this spectrum. Now, light or electromagnetic waves can do a couple things. They can bounce, they can be absorbed, or they can bend. First, let's talk about reflection. Reflection is basically where the light is going to bounce back into the medium it came from. So that means if it's in the air and it bounces on a mirror, it's going to reflect or go back into the air. So it was in the air, that was the medium. It bounces and goes back into the air, which is the same medium. Reflection you already know about most likely, but let's look at the law of reflection. If light comes in and hits the source right over here, all right, if we draw a line perpendicular to the object we are going to hit, that is called the normal. Now, the angle that the light hits at from the normal is actually equal to the angle it reflects at just on the other side of the normal. So the angle over here is going to be the same as the angle over here. They just mirror each other across the normal line. All right? So that's the law of reflection. If we have refraction, that means that light bends. You've probably seen this before, putting something in water. It looks totally different above the water and below the water. The reason is light travels at a different velocity in the air versus in the water. Once you get that look of both mediums at the same time, you see that light bends or it refracts. So when the light comes in and it hits the new medium, it's going to bend at a different angle. All right? That's called refraction. Diffraction now is slightly different. That's where light or electromagnetic waves are going to bend around the corners or edges of an object, or they'll bend through a little slit. So if we look at these pictures, we can think of it like waves in a pond, but remember, we're also talking about electromagnetic waves, waves we can't see. But if they go to the edge here, they're going to go actually through the slit and then spread out. If they hit the edge over here, they will move past and then eventually spread out again. That idea of spreading out after going around and bending around a curve is called diffraction. Now, if you go through two slits, the interesting thing is the waves start to do some cool things where some of the waves cancel out and some of the waves actually get larger. And we'll talk about that when we talk about interference in the next slide. Interference here is simple. We've learned about that from our Slinky lab earlier. But if two waves are oscillating basically in the same way, they are going to combine to make an even bigger wave. That's called constructive interference. If two waves are oscillating opposite of each other, then they're actually going to cancel each other out. And that type of interference is called destructive interference. If you take a look at these two pebbles dropped in the water at the same time, we know their waves both go outwards. But where are there constructive interference for waves and where is there destructive interference for waves? Well, if you look at these white parts right here where the waves look a little bit flatter and don't cast as much of a shadow, that's where the waves cancel out, or what we call destructive interference. All the other parts where the waves look pretty prominent and easily defined, That's the constructive interference part. All right, the last thing we're going to talk about then is polarization. If you take a look at light here, light, though it is electromagnetic wave, it can be oriented in a lot of different ways. It can be oriented up and down, left and right, on a diagonal. So all of a sudden you have this light, these waves, all going in different orientations. Well, that creates a glare. But if you use a polarizer and you can polarize the light waves, you can actually reflect, absorb, or just filter out all the orientations of light that you don't want. So for example, right here, notice that this is a vertical polarizer. So all of the oriented light that doesn't go vertically gets canceled out, as you can see in the second part, because now only the vertical light comes through. Why do we care about that? Well, if you wear sunglasses that are polarized, by filtering out a lot of the different orientations of light, you can still see well during the day, but there's no longer a glare. You don't have to squint, and things are a lot clearer. If you tried it with a rope through a fence and just jiggling a rope any which way, if the fence was only vertical slats, it only allows the vertical waves to go through. All right? But if you tried it this way, only the vertical could come through on the first part for this polarizer. If it only allows horizontal, the next one, but only vertical waves are coming through, it cancels it out. And that polarizer totally eliminated all the waves. So polarization is actually quite helpful for things like our windshields and sunglasses. And if you're a fisherman, you definitely use fishing glasses, which is basically a fancy way to say you have polarized glasses to see deeper into the water because it eliminates the glare. Here's the last thing we want to look at with polarization. When the sun hits the ground, it creates a glare, and it slightly actually polarizes the light, but that glare is still there. Luckily, if we wear sunglasses, our polarized lens can cancel out some of those different angles of the light and only give us what we're looking for through the polarizer, which can allow us to see the light that's useful without creating a large glare and having to squint. All right, today we covered the electromagnetic spectrum. We talked about how electromagnetic waves are formed and why they exist. And then we talked about different forms of light. Remember that they can reflect, refract, diffract, and we can use a polarizer to help cancel out unwanted waves. All right, thanks for listening. Best of luck.